I wonder what happened.
With breaking the.
Huh? Yeah.
How's it rate?
Get pretty much nothing that I plan to do. So comes up. Working on all my linears.
You have linear algebra?
Yeah. Taking it as an independent study with women,
I see.
so it's very easy to neglect.
Yeah. Oh, yes.
And then, but I had done like 3/4 of what he wanted turned in
Mhm.
by today. I wasn't too worried about it, and then I just had like a couple proofs I needed to figure out. And then I got to like the fourth assignment, and then I was not as prepared for that one. Maybe I did all right.
Okay, so this is after spring break. Hopefully we were doing okay with chapter 5 and 6. I haven't really finished grading the midterm, but the midterm is due on Wednesday. I'm supposed to turn it in. So I definitely have to finish the grading. We'll see. You can always retake it if you're not happy with the number after we have to grade it. Right, so basically before the midterm, we finished chapter 5 and 6. So after midterm, we're gonna start with chapter 7. And this is the plan for today. Did you guys see Gregory?
No, I haven't seen.
Let's see. All right, let's start. Oh, I forgot to turn this on. So basically, chapter 7, we're moving on to interval estimate. So if we think about the content so far, chapter 5 is really the theoretical foundation for many of the things that we do in statistics. So it's really a bridging chapter. Before chapter 5, mostly we're working on probability formula. And then after chapter 5, we're working on statistical procedure. So chapter 6 is a lot of estimation formula, estimator. So we have to study estimation method, the quality of the estimation, how we come up with a good estimation for the parameter. So most of the majority of the content in chapter 6 is on point estimate. Chapter 7, we're moving on to interval estimate. Instead of using a single number to make estimation, we will be using the interval for the estimation. Now, chapter 8 will be working on hypothesis testing. So these are the plan for the whole book. Chapter 9 will be more hypothesis testing. So we spend 2 chapter hypothesis testing. That's chapter 8 and 9. We spend 2 chapter in estimation. The point estimate for chapter 6, interval estimate for chapter 7. And then chapter 5 is many of the statistic. So the statistics, the T statistic, F statistic, these are all defined in chapter 5. If you still remember. So basically T statistic is you have a standard normal variable divided by a chi-square variable, square root of the chi-square variable. And the F statistic is a division of two chi-square variables. That's kind of the main idea. Now, section 7.1, the title is confidence interval for population mean. So the parameter we're trying to estimate is a mean for a quantitative data. So try to use the interval to estimate it. That means we have to create a lower bound and upper bound for the population mean. Here we are. Right. So this is a theoretical reasoning for the formula that we'll be using. Okay, so suppose you have a mean that you want to estimate. The mean is the mu, the letter mu that you see here. Suppose we have a normal distribution which has a mean mu variance sigma squared. And how do we do it? If we want to make an estimation, we have to select sample population, assuming we have an n sample, x1, x2, xn, all numerical value, and then the estimator for the mean will be x bar. Okay, we have already talked about the estimator, the maximum likelihood estimator for the population mean, which will be the x bar. And so that's a point estimate. So chapter 7, we're going to try to think about a way to give a interval for the mu interval for the one of the starting point would be x bar. And then another thing to do is to look at related the distribution of x bar. Since x bar is the estimator, we're going to find what kind of distribution x bar has. That will allow us to have a formula for the lower bound and upper bound. So what we do is, what exactly is x bar distributed based on, I think it's 5.5. 5.5 mentioned many of the distribution related to normal distribution. So x bar is normal with mean equal to population mean, the variance equal to population variance divided by n. That's what we have. So that gives us a formula related to how do we construct the interval. We want an interval that has a 90% of the 90% of such a percentage. This percentage we can consider as a probability value of 1 minus alpha, alpha being a really small number. So 1 minus alpha is a big percentage, a bigger number. And that represents the percentage of this distribution within these two boundaries. So I'm drawing the bell curve here because in this example, we really are looking at a normal distribution. So alpha is 1 minus alpha is in the middle. So the total value of alpha represents the percentage outside this boundary that we're searching for. So because we know the mean for x bar, we also have its variance. So if you take x bar minus mu divided by the square root of the variance, which is sigma, and you're standardizing x bar. And that's according to central limit theorem. Also according to what we have in 5.5, this is a standard normal variable. So x bar minus mu over sigma over movement, that's a z. So based on the distribution of the z, so within the z alpha over 2 and negative z alpha 2, the total percentage will be 1 minus alpha. So last line on this page is understanding of the distribution of z, like the relation with z alpha 2. Any question? Oh, you okay? Any question? So the reason that we mentioned that, because it gave you a natural boundary of the interval. Basically, negative z alpha over 2 and the positive z alpha over 2 is the central, like the lower bound and upper bound of the central percentage. You can consider this as the confidence interval for z, but then with that, you can multiply both side equation with the denominator and then move the x bar out of the subtracted. So then we will be able to create a natural boundary for mu. And that was the reason behind this. Okay, so take the probability inside the probability equation on the bottom line here. I'm gonna take that inequality and start creating a interval, like lower bound and upper bound, because you have a natural lower bound, upper bound in that inequality. Are we okay? So then we work on the algebra. Take this inequality, we multiply both side equation with the denominator, then we get here. And then we multiply or add, subtract the x bar from both side equation. And then we switch the negative sign, multiply the negative sign. Then we have, that's the upper bound and this is the lower bound. So the last line of the formula is giving us a boundary of the population mean. So population mean will be in between this upper bound and that lower bound. That's our confidence interval formula. Any question? So the confidence interval formula will be sample mean minus c times the standard deviation over root n. It's lower bound. The upper bound is sample mean plus z times standard deviation over root n. That's the upper bound. So that's our confidence interval formula. Let's look at how do we apply the formula. In this page, right in the middle, that was the formula. The z there is related to what exactly the kind of confidence you wish to have. For example, if you want a 95% confidence, then the outside 95 is 5%. So if the middle of the bell curve is 95%, then the alpha is 100% minus 95%, which is 5%. And that's the total on the outside of the interval. So each side of it is going to be alpha over 2, which is 2.5%. So we're going to have 2.5% there and 2.5% there. The boundary, this is z 0.025, and that's negative z 0.025 because the middle is 0. Okay? Try to indicate what z are we requiring. So the lower bound is x bar minus z 0.025 times standard deviation divided by the upper bound is x bar plus all that, and that's giving us the calculation method for the interval. Any question? We resolve this question, we need x bar. So in this question, we will already mention that the mean is 1,478. So that's x bar. The standard deviation is also given. The variance is 1296. Now with the variance, you take square root of the variance is 36. So take square root of the 1,296. We get 36 of the variance. The sample size is 27. So take root of 27 function. So that kind of lead to the final calculation. The rest of the answers already on the page. Do you have any questions? So this is an example illustrating how is the confidence formula being applied. Now, the previous page explained the reasoning behind that formula. It's from this probability equation that indicated how do we capture the middle percentage of the x bar distribution of the mu thing. All right, so how do we understand the confidence interval? All right, so if you use this method, you will be able to calculate the lower bound and upper bound, which should be an interval. Our idea would be the mean, the population mean mu we're searching for should be in that interval. But there's an uncertainty because the interval is calculated using your sample. Depending on how well your sample is, this interval, the last line, this interval may or may contain the true population mean, but as long as the likelihood for it to contain the mean is high enough, we say 90% confidence that this contains the population. That's why whenever you calculate confidence interval, you always have to specify the level of confidence. Higher confidence certainly is better than lower confidence. Here we have. If you calculate many such interval, about 90% of them should contain the population mean. So we're not guaranteed the interval that we constructed had the mean in there, but we are saying that 90% of those intervals contain the mean, which is a very high likelihood. Question. So that's just the interpretation of the results Right, this is an example from the book. We have using the same formula. We collect multiple sample. Every time we have a sample, we have a different sample mean, different sample size stay the same. But we construct a 50 interval because the mean is different. Mean really control the location. You can see some of the bar are further to the right, some of them further to the left. And this one does not have the population mean is at 50. Some of them have the population mean. This two does not have one. And then these, I mean, those are the interval that had the mean in between the lower bound and upper bound. And there's 1, 2, 3, 4, 5. So there are 5, 6. There's another one that doesn't have the population mean, but most of the interval have the population mean in the interval. Any question? This is the 90% interval, meaning that out of 50 interval that we constructed, 45 contain the mean. That's what we mean by 90% confidence. Let's talk about length of the interval, which is really from the lower bound to the upper bound. The entire length is twice the margin of the error. All right, so what we did is to take the, so there are many factors that affect the width of the interval. X bar plus the alpha over 2 times the standard deviation over n, right? And then x bar minus z times standard deviation over n is the lower bound. So the entire length, half of it is being called E. E is margin of error, ME or E, margin of error is z times standard deviation over n. And so all these numbers are going to affect the length of the interval. For example, if n goes higher, then the margin of error will be smaller. So then if you have a smaller margin of error, you have a more accurate interval. Sample size affect the length of the interval. Sample size high, the length of the interval go down. Another one is the standard deviation. I mean, we cannot control it. But if the standard deviation is smaller, then we have a more accurate interval, or the margin of error will be smaller. Another thing is Z. Z is related to the confidence. If you have a higher confidence, like 99 confidence, then Z will go up. If the confidence go up, then Z will go up. And then the margin of error will also go up. So these are the couple of things that will really affect the length of the interval. Any questions? So this try to analyze what's causing the change in the interval. We certainly would increase the sample size to lower the margin of error to bigger sample size give us some more accuracy to look. All right. Another thing will be, what if the distribution is not normal? When we first starting this section talking about normal distribution, trying to figure out the mean, then sample size is 5 is okay because we already know the data are normal. If the data is not normal, we have to use central limit theorem, which means we have to have larger sample size. Whenever the sample size is larger, that means we have to collect more data and it's more time consuming. There's more calculation. So we definitely wish to be able to guarantee the data is not normal, then we don't have to work on central limit theorem. But if the data is not normal, or if we cannot guarantee the data is normal, in order to apply central limit theorem, we have to use larger sample size. Any question? Occasionally, people are talking about how we apply central limit theorem. How do we use smaller sample size? Again, symmetry is one of the things. If the data are it looks like the histogram are mostly symmetrical, then smaller sample size will be okay. Unit model symmetrical data, then we can relax the requirement on sample size in that case. But the rule of thumb is at least 30 in order to have large enough data and apply central limit theorem. Okay, so this is one of the examples. There's a lot of historical statistical research where the sample size is large. If the sample size is large, you no longer have to worry about the distribution of the data. This is talking about, actually put the amount of orange juice. Suppose it's known that standard deviation is 96, we want to estimate the mean. Assuming that a random sample of 576, we have a 133 grams of juice. And from here, we're going to construct 90% confidence interval. So we have 90%, the z is 1.645. So z is directly related to the confidence level. Are we okay? Do you have any question? Okay, so the sample mean plus or minus the z times standard deviation divided by square root of the sample size. And that's how we can calculate the lower bound and upper bound of the interval. Any question? Okay, so these are the formulas. Let's see. Question. All right, so this is one of the questions asking us to construct 95% confidence interval. The population mean is a sample mean. The sample mean is 235. The sample size is 75. I have the formula already on the board. The population standard deviation is 28. So let's do some calculation. For 95 confidence, Z should be 1.96. So size is 75. The X bar is 35. Standard deviation is 38, 28. Already have the answer.
I don't know on that.
Have the answer. The calculation. So we will have 4 X bar, the Z, the Z, 95%. That means they put 1.96. 95%. You don't have the card. You forget the card.
That's all this stuff.
No.
No. Is this right?
Yes. I'll find your card. So you can take a picture with your phone. Oh, not that one. Card.
It's so weird.
Do you remember your number? It's yes. Yes, I do.
You go alphabetically, I guess I'm number 1. Then you like randomly do that.
Yeah, I think I was using the last name too. Yeah, so you should be number 1 then. Well, let me picture of it and then we can scan. Ah. Yours is number. You're the number one.
Yeah.
Oh. So let me actually find out who's number one. It's not easy.
You want me to just go into the meeting and type my answer?
It's two. Yeah. Make a square, make sure the angles. Take a picture.
Yeah.
Let's try and see if we can scan your answer. No.
Let's turn on screen.
No, it didn't scan. Let me try again. It is. Anyway, let's see.
Sure.
Okay.
I'll keep that picture safe.
All right, let's continue. So what about when the population standard deviation is not known? Then we have to use our data. So you're gonna take your data and try to find the standard deviation, the sample standard deviation. And we all know how to find the sample standard deviation. Do you know how to find standard deviation from data?
Expectation X squared plus expectation X squared.
Yes.
Or
Right.
X squared.
Yes. All right, so we're gonna use our sample standard deviation, and we talked about that in chapter, I think it was chapter 5, section 5.6. 5.6 or 5.5. So x bar minus mu divided by sample standard deviation over root of n. This is a standardizing process, but replacing the population standard deviation with sample standard deviation, this is what we call the t statistics. So it's rough when the sample size is bigger enough, applying central limit theorem, it will be almost normal. But for smaller sample size, we'll have for smaller sample size, we have to use a t distribution. So this is a couple of scenario. Number one says we have a sample size of 32, so we can apply central limit theorem. In this case, we can use a sample. This is a sample variance, so sample standard deviation is square root of the 10.60, and we have the x bar. So x bar is the center of the interval. So x bar plus or minus the margin of error. So this is the first scenario. If you have large enough data sets applying central limit theorem, we can still use Z. However, another scenario is not having. If the sample size is small and we don't have population standard deviation, then what we have is x bar minus mu divided by sample standard deviation over root of n is what we call a t distribution. That's for the smaller sample size. If you have a larger sample size, this is roughly normal as well. So basically, t distribution have a very similar shape to the z distribution, to the normal distribution. Except the degree freedom, the t distribution, the denominator is a chi-square distribution, of the degree freedom of n minus 1. So when sample size is not large, we have to differentiate from t distribution to the z distribution, which is not guaranteed to be a normal distribution, but we can still have that probability for t to be bigger than this t alpha over 2 is alpha over 2. So that will allow us to find out the outside percentage and the inside percentage. So we have an interval with a t, and then the calculation will be instead of a z, you'll be using the t, and then you have to grab the t table, and with the t table, you have to have the degree freedom considerations. So there's a little bit more discussion on the t, like using this example. If you read through this example, we realize the sample size is 20, so it's not guaranteed with central limit theorem, and therefore we use sample standard deviation, we have the sample mean, and this is a raw data. Middle of all these numbers are the data. From this data, we can calculate the mean, we can calculate standard deviation. And now it's time to do the calculation. So have the mean plus or minus, and here we use t times standard deviation divided by h squared root of sample size. And how we determine the t? There's many t curve because there's many degree freedom. If the sample size is 20 minus 1 is 19. So in the t distribution, you're gonna look at degree freedom equal to 19, and the percentage, the central percentage is 90%. So the outside percentage alpha is 10%. 10% alpha have to divide it in half. So half on the left, half on the right. So have the 5% t. That's what we really needed. So it ended up being 1.729. So that's how you calculate it. So the rest of them, once we realize what number to use, the rest of them are just calculation. Any question? So the main purpose of this example is to decide what kind of t we're using. How do we determine the t? For this, we can use a t table. A t table can have column and row. The row are listing the degree freedom. The column are the tail percentage. In this case, it's a 0.05. That's how we determine which t value are we using in the t table. So t table, unlike v table can handle any v value, but t table only has special value of the t. It doesn't, so there's only a limited number of t value that you can show on the table. So it's not as extensive as the t table. Okay, so again, we can use R as a way to do the calculation. For this one, number one is you have to enter all your data, right? So all these numbers, we enter them into our code. So then first thing is enter the number. The function length, and that identify how many number is in this data set. And this line t equal to qt is quantile from the t distribution with tail being 0.05 and degree freedom is n-1. And identify sample size using the length function. And then we can calculate the interval. Calculation goes mean of this data set plus or minus, we go negative t, positive t, plus or minus standard deviation of your own data set divided by square root of the sample size. I'm using n to represent sample size and already have a value for it. And then of course you can on R, in R coding, we have a function called the t.test. It does the t-test. So if you run the t-test using your data, with confidence level equal to the 90%, we will give you the same result. Any question? The t-test is faster, but this is your own calculation. It will give you the identical answer to the interval. Any question? Right, so the interval that so far we were doing, they're all two-sided interval. Start with x bar, you go minus and plus. You have two-sided interval. So therefore, this interval have a lower tail and upper tail, left tail and right tail. And sometimes when you are looking at a number, you only want to find the upper bound. You only found the lower bound. In that case, then we may want to look at how to calculate a one-sided interval. So far, all the interval we did are two-sided interval. When do we need a one-sided interval? For example, Let's say you are looking at a quality control of a institution, where let's say you are making computer, most of the computer will go out onto the market if it functions well, but then occasionally you have defective computer that you have to not sell. You have to make it separate them apart and start rebuilding or fixing it. So the number of percentage of defective computer are low. I mean, if we have a large percentage of defective computer, we have to worry about the facility, right? We have to like rechange the. So in that case, the percentage of defective computer will be a percentage that we want to calculate the interval. So those percentage we definitely only want to find its upper bound. Right. The lower bound for defective part is 0. That's when you don't have any defective part, right? So in that case, the only interval, the boundary is the upper bound that we want to find out, because the lower bound is 0 anyway. Any question? So that's the kind of situation. The number is so small, and the only concern is the upper bound. When the upper bound is too high, and that's when is alarming. That's when people have to fix things. Other things that we only want to find the lower bound is when 100% is more popular. For example, our school have a very good nursing program, so most people will pass with like 100%. Right, so then in that case, you want to find the lower bound, right? With the lowest score. So if almost all the students pass with 100, then the few score that didn't pass with 100 will be the concern. That's when you only want to care about the lower bound. Am I making sense? So sometimes only want to find one-sided interval is possible scenario. So how do we find the one-sided confidence interval? We actually already had a two-sided interval. Let me try to go over logic. So the formula really is derived out of a two-sided interval. So the two-sided interval we get is this. The upper bound is x bar plus z times z or t times standard deviation over n, and then the lower bound will be x bar minus z times standard deviation over n. Now, what if we want to find one-sided interval, for example? If we only want to find the upper bound. Okay, so how do we calculate the upper bound? It will be x bar plus z times standard deviation over n, but then there's a little difference here. And if you want to create a two-sided interval, this is alpha over 2. This is alpha over 2. And the middle is 1 minus alpha. So we're using the alpha over 2. It's the outside percentage, it's alpha over 2. But if you have a one-sided interval, then this is alpha. Okay, so then we need the alpha instead of. So this is a one-sided interval where only the upper bound is a concern. So if you only want an upper bound, our upper bound, and the lower bound, of course, could be negative infinity. It's really not a concern. So that is a one-sided interval. Notice that the only change is the alpha. If you have two-sided interval, you have to have alpha over 2. But if you have a one-sided interval, you're going to use the alpha. Are we okay? Now, if you want to have a one-sided interval where it's the only lower bound that you are concerned, then the lower bound will be x bar minus the alpha. Remember, it's going to be the alpha, not alpha over 2, because it's one-sided. And then standard deviation over n. And of course, the upper bound will be infinity, because we're not concerned about the upper bound. We just want to find the lower bound. Those are the one-sided interval. Over here on the left are the two-sided intervals. Just trying to compare number that we're using for different kind of interval. Any question? Hope that kind of makes sense. So somehow we might want to consider the one-sided interval here. process. All right, so if you only want to kind of calculate, determine the one-sided interval, the probability for it will be, so within this is our boundary, so the upper bound is alpha, and then the majority is 1 minus alpha, it's a lower percentage. So for this, this is we only want to find the lower bound. So this number x bar minus the times the division over n is less than mu. This probability will be 1 minus alpha. And then this boundary is just a lower bound for mu. Another scenario is negative infinity to x bar plus the alpha times. So that's when the only concern is the upper bound in question. So that's the formula. That's the formula. You only want to find the lower bound, right? This is the formula. The last line of formula is when you only want to find the upper bound or lower bound. In any case, the upper bound is x bar plus the margin of error. The lower bound is x bar minus the margin of error. So it's the same thing, two-sided or one-sided company interval. The only differences is the z in question. So those are the one-sided company interval formula. These are the homework for 7.1. There are 2 that with even number of questions. 3 of them are odd number questions. Are you okay? This section, most of them are statistical work. We don't have a lot of theoretical considerations, so it shouldn't be that difficult comparing to chapter 5 about theories. And 7.1 and 7.2. It's also comprehensible. Um, 7.1 and 7.2 are closely related, but 7.1 is counting both the differences of 2. And then these are the kind of things that you might, I mean, counting inputs. You guys did this kind of work in other statistical class? Have you done counting interval before? No? Okay. So then we may have to pay attention. All right, so the counting interval for one population mean you can use the z value as a margin of error calculation, or you can use t. I guess I should explain more if we are not quite as familiar with it. We already started mentioning this formula here. Let me try to isolate this. All right, so what we have here is taking the x bar, add or subtract. The one that we are add or subtracting, this one, we have a special name for this. It's called the margin of error. Because if you're estimating something using your sample mean, of course, there's no guarantee it will be exactly equal with x bar. So then we add, subtract a margin of error to give a little spaces, a little flexibility for the estimation. That's the margin of error. This is using z. Of course, if you don't have population standard deviation, you'll be t. Another formula will be using the x bar. Using the x bar to minus t times sample standard deviation over n for the lower bound, and using x bar plus t times the sample standard deviation over square root n the upper bounds. That's z approach or t approach, depending on what the population standard deviation is given. If you have population standard deviation using the z approach, if you do not have population standard deviation, you're using sample standard deviation, and you'll be doing the t approach, the t interval. for the company or one mean. So all these are trying to figure out exactly what would the mean. So which the answer will be the mean is between this number and that number. And this is how we provide a interval estimate for a parameter. Now, what was the 7.2 really focused on is pairing. So instead of having one mean, you want to find out the value of that one mean. The confidence interval for the differences of two mean is aiming at comparing. Difference of two mean is mean one minus mean two. We want to find exact value of mean one minus mean two. That's really what was the goal of the calculation. Right. So we're going to look at a couple of examples, and the difficulty in 7.2 is because we're looking at two separate data sets. And so there are differences in the data set, also in the population behind those two data sets. What if they're similar? What if they're really difficult? What if they are not normal? What if they are not normal? So there are differences in the area we look at. Case number one, and it's when both of the data are normal. I mean, this is the best situation. If they're both normal, it's guaranteed the data are, we can use the value. It's guaranteed that they have similar behavior. So here we have an example. The story behind it is we have lengths of female and male brain blendings spiders. So it's a length of spider, two different kind, X value and Y value represent length of spider. We want to find approximate one-sided 90% confidence interval. That is a upper bound for mu X minus mu Y. So another thing is we're not trying to find a two-sided interval. We're just looking for a one-sided interval. That means the alpha is 5%, we need a 5% D. So the alpha do not have to be divided by 2 since we're only looking for the one-sided interval, right? So after realizing those data, we should be calculating the estimating the differences between the two populations. All right, so when both of the data are guaranteed to be normal, so what do? I mean, you read the question more carefully. This is a second example in 7.2. The question already stated here that the lengths of the spider are approximately normal. So normal distribution has already mentioned and confirmed. So if they're both normal, and of course we have normal distribution for both of the set of data. So X is normal with its own mean, its own variance. So Y is normal, and therefore X minus Y is also normal. So this is something we mentioned in section 5.5 when you are guaranteed to say normal distribution. If we have normal distribution, then we use we have used central theorem. So X minus Y is normal. And the mean for X minus Y is mu X minus mu Y. The variance is a summation. So that is something we practice in 5.5. And then another thing is X bar is normal because X is normal, so X bar is normal. Y is normal, Y bar is normal, right? On top of it, X bar minus Y bar is normal. And then the mean of this will be mean X minus mean Y, and the variance will be summation of these two variables. So why are we talking about this? Because we are trying to find the Z of the X bar and minus Y bar. So then we can see X bar minus Y bar minus the subtraction of the two mean divided by square root of their combined variance. We'll be able to find the Z value. So if you have a Z value, we have a probability equation. With a probability equation, we have an interval. So rooted in the fundamental understanding of it. So with that, because X bar minus Y bar is normal, so the mean X minus mean Y is between X bar minus Y bar minus the margin error, X bar minus Y bar plus the margin error. So we have this confidence interval formula. So here we are. So this is our first formula, and the theory behind this formula is we know for sure we have normal distribution. That's why the Z is being applied. And notice that this is a two-sided interval. If you're doing one-sided interval about the upper bound or lower bound, you have to use the alpha. Whenever we use the alpha over 2 is because we are doing a two-sided interval. Occasionally, the question do wanted to have one-sided interval or two-sided interval. We have to pay attention to the wording. And any questions so far? So number one, if we know for sure the data is normal. Number two, if the sample size is large, we can also use the, because central limit theorem allows it. All right. Now, we said we're gonna try to find a one-sided interval. For example, if you're gonna find a one-sided interval to determine the lower bound, this is what we have at the bottom one. The top one is a one-sided interval for the upper bound. Upper bound is point estimate is x bar minus y bar plus the marginal error to get the upper bound, and the lower bound, of course, will be negative infinity if you only want to find a numerical upper bound. Any question? So from here, we're gonna look through the example that we were doing earlier, which was this one. Right? I introduced this question because I want to use this data for calculation. So we could load the data from a file. The file is online in a data set. This is how you can load the data into from a file into your data set. And after you load the data set, because the file actually have two data set, you might have to identify the column. And I guess we can try this. Oh, hi, I see that you are online. And you can answer the question. I wonder if you how early you are. You can answer the question by typing your answer in the chat, or I can send you the link. Let's so turn on. If you're still online, this is your link. You can answer the question by clicking on the link. That way, the clicker question is over here. It should be a C. Turn on the scanner. Okay. So thank you. Right, back to the question. You can see the data is in the 7.2 question number 5. You can find the data set online and actually post data set in here. Right, and let me download this data. So that you can see. You can enter all the data and you're gonna go to section 7.2, number 5. So these are all the number that we have. It's in a virtual format, unlike what was in the textbook. It's what it is on the textbook, like X start from 5.2, Y start from 8.25. The same data set. So what do we do? One thing, if you want to do this, you have to download the whole file, and you also, if you want to use this is our code that was made by and write down. This is the scenario that you can read the table from a file. Then you have the file downloaded. I normally download into download, and then add header. There's no header, so header equals false. So then you actually load the 2 column into your data set. I think we tried it before. Did we try this before?
In terms of like importing the data,
Yeah.
yeah, we've done that a couple times.
So you end up having a column data. So then the column, you have to identify the X value and Y value from the column. So anyway, if we can also do it now, since I have the data already downloaded, I just want to illustrate how do we do it. So this is the data set. Since I already opened it, I can copy and paste this. That is really I don't have R on this computer. Installing it on the computer takes time, so I'll just run R code online. Right, so we're gonna enter data, I guess we have to do the read table. See if it works. Read table, and then this is enter text to. All these number, and then I wonder if I have to write into the text. Let me make sure my syntax is okay. All right, well. Right, I wonder if this works. Try to read between the line. It works. So if we are using read table like inline text, this is what happened. Now, if you want to use read table from the file, this is when we have to, if you use read table with file, you have to have R already on the computer. I'm not doing that because I didn't install R. And if you have to use it online R coding, you're making this as your calculation engine, then they don't have your data. So if you load it from here, it's not working. This app will not access your local data. It can only access what's already in here. So I'm doing this. All right, so we're still doing read table, but you can read table from the file, you can read table from the text you type in. And after we've done that, if you want to display, it looks like this. So it's kind of similar to if you want to read it from file. So end up having this. And this is what happened when we don't have a header. So you can see the header is called V1, V2. And that would say X and Y. So one thing we can do is actually add headers. So we know which one's X, which one's Y. So X and then Y. And that way you also have to explain that you do have a header, you go header equal to true. That way when we run it, we actually have the header in the output. So that's what happened after. Okay, but then they are still vertical. It's going to be hard for it to do it. So what do? We can do this. Oh, there's X. All right, I guess there's a confliction, right? I call this column X. I also call the data X. That's not very good. So instead, let's call that data. All right, and then after we've done that, it won't like the right thing anymore. So we will display the data instead. Instead of changing the name. So this is all the data. So how do we call that? You can see, let's call X equal A equal to data. A equal. All right, A equal to data, and then you do a $sign to call the X. So that's all your X value, and then B equal to data. And there's a $sign. So then we use a $sign to identify a specific column. Are we okay there? So this is changing vertical vector into a horizontal vector. So this is what happened. And then let's call, you display the A and then display the B. This just assign those values to the column, but it won't show it. So those are input language, and I'm doing A, B to make it output. So see what's the output. We've done that. This is the output. Did I not remove that line? Well. Okay, so the outcome is these are all the X value. Down here we have the Y value. It's not displaying the same way, right?
This is
the
spaced
X.
out, the Y.
Yeah, the Y when
Double
actually,
spaced.
yeah, the space is different. Weird. Anyway, now we can actually do calculation. According to our formula, we need to know the mean for X, the mean for Y, the variance for X, the variance for Y. All these are necessary. So the calculation will be the mx is a mean for the A data or the X data, my the mean for, I'm just naming it in the more convenient way. Those are the mean for Y and mean for X, and their variance for X. We use VAR of the A data and variance for Y. VAR is a function name. So this allows us to do those calculations. We don't have to display them anymore. And the formula is right here. This is our formula. So we're going to do a one-sided interval. I guess we were calculating. Let's go back to the initial page. We're trying to create a 90% counting interval, one-sided counting interval that and it's only the upper bound. So we're only looking for the upper bound. So if we're doing the one-sided interval for the upper bound, it's a top formula, right? So we need mean for X, mean for Y, variance for X, variance for Y, sample size for X, sample size for Y. That's all we need. So the two mean, there's two variance, there's two sample size, there's a Z. So altogether we need 6 number. Are we okay? So we're gonna apply this formula to construct the upper bound of the interval, which is only a single number. We only have 1, 2, 3, 4. And then the sample size, let's call that NX, sample size for X as all the length function of the A or the X data, sample size for Y, and that's the B data. So now we have 6 number. Now we need a Z. And it's the Z for the 90% count. What's the percentage again? It was 95%. So to create the 95%, I think we have it over here. What was the 95%? We only want the upper bound. This is 95%. So the boundary is 5%. We need the 5%, Z 0.05. Okay, so we're gonna do, it's gonna be a Q norm, a quantile in the normal table. We have 0.95. 0.95. That's the Z we're looking for. And then we can start constructing the interval. So how do we have mean for X minus mean for Y plus a Z that we find out, multiplied by square root of the variance for X, Vx divided by Nx. Variance is already standard deviation squared plus the Vy over the Ny. So that is the variance over sample size, variance over sample size added together. Let's combine the variance. The summation of the variance, square root of summation of variance, that is a standard error. Z times standard error is marginal error. So there's a calculation, and this is a result. And that was negative 1.828. That was the answer to the question. Should be everything we did. So it's really X bar. I did an X bar, Y bar on this layout, and on the I did an X and Y on the article. But anyway, I hope that kind of makes sense. The question. You can see that E is calculated by Z times square root of Vx over V. So then I'm calling that E. So next time when you do the calculation, it is already calculated. So those are the language on this file, but you can change the name, you can calculate whatever that was convenient and clear to you when you try to do mutation. Any question? Are we okay? So that's the answer to question number 5. It's actually one of the homework questions for 7.2. So I'm using basically that exercise as case number 1 when the normalness is already mentioned, so we don't have to worry about guarantee the normal of the data. All right, and now this is case number 2 when you have data that's not normal. However, we have a large sample. So according to what we said, if the sample size is large, and we're guaranteed to apply central limits here, so we can still use a Z value, and it's because it's a large sample. So we're just taking care of the easy situation and probably moving on to the harder situation in case 3, 4, or 5. Right, so what we do here is a scenario, and we don't have the raw data in this one. And this is the easier one for our math major, but it's probably harder one for the student that are used to having data there. So we want to find a one-sided approximation of 90% confidence interval that is a lower bound. So if it's a lower bound, it's x bar minus y bar minus z times the square root of the combined variance. And here we do have the x and x equal to 60. So sample size for x equal to 60, the x bar equal to 77. Standard deviation is 129. The sample size for y is 60. And the y bar is 480. This is all from the textbook because I don't have a way to write the x bar, y bar. So I just write words, x bar, y bar. On the textbook, they actually have a bar on the letter. This is the second question. The calculation has very similar process. And so here are the calculation. You identify x bar, y bar. We're naming those with number, variance for x, variance for y. That's the square of the variance. And the next one, you want to find the z. What's it? This is 95% confidence. In that case, the z was wrong. We should use a Q norm of 0.05, not 0.025. Because the 95% confidence, so alpha is 5%, not 2.5%, because we don't do two-sided interval. For one-sided interval, the alpha do not have to divide by 2. So I guess that was an error there. Every semester I thought I should change my mistake, and then I keep forgetting it. It was 0.05, right? And then sample size is 60 and 60 for both. So you can see the square root of variance over sample size, variance over sample size is combined. Variance, square root combined variance is standard error times the is the margin of error. So that's margin of error calculation. X bar minus y bar is a point estimate plus the margin of error. Then that's not right. We are looking for one-sided approximation, 90% confidence for the lower bound. If we want to find the lower bound, this should be a minus sign. So it's minus c. That's the correct method for the computation. Any question? Okay. So there should be x bar minus y bar minus e because we're looking for 95% confidence interval one-sided with a lower bound identified for the lower bound. So it should be minus e instead of plus e. That example. All right, case number 3. So case 1, case 2, you either have a guaranteed normal distribution or you have a really large sample. And that in that case, we use z. But then here we are. Case number 3 is when we have small sample, population standard deviation is not given. I mean, if it's population standard deviation given, of course, we'll be able to use the z procedure. This situation saying but we still have normal distribution. We don't know the population standard deviation, so we still assume data are normal, and then they have the same variance. So this is a case number 3. So we're going to try to lay out what happened in this situation. I mean, number 1, if we have normal distribution, so x is normal, y is normal, so x bar is normal, y bar is normal. In that case, when you subtract x bar minus y bar, because x bar, y bar already normal, so x bar minus y bar is still normal. So, and on top of it, we have this scenario. We assume their variance are the same. So you can see x bar have this variance over sample size, y bar have this variance over the nx. So we assume they have identical variance. That's like one extra thing in this assumption. And because we want to compare variance, because we have 2 different data sets. And that's something we don't have to worry about if you only have one mean. 7.1, you want to create a interval for one set of data, one population, with only one standard deviation. But 7.2, you have 2 set of data, 2 population. Do they have the same variance or do they have different variance? That's the case 3, case 4. So I have to separate into 2 different scenarios. All right, so This is about a small sample though. If you have a large sample, none of these are a problem anymore. So anyway, they assuming they have the same variance. So when you combine them, you add that variance with this variance. So the combined variance is sigma squared common factor multiplied by 1 over nx plus 1 over ny. So now how do we normalize? We have our x bar minus y bar minus the mean, right? And divided by standard deviation times the square root of the combined 1 over nx plus 1 over ny. So it looks a little bit weird. It's all because it's assumption that they have a common variance. They have the same variance. So after normalizing, we now have a z. In comparison, the default assumption is mu x minus mu y. Actually, it's the one we're estimating. Anyway, after we got this, what we're gonna do is, since we don't have the standard deviation, so this is like temporarily. This third equation in this page have the standard deviation, but we do not know it. See, we do not know population standard deviation, even though we assume it's the same, but we do not know it. So we have to find a way to get rid of it. So what do we do? Here we're going to do a chi-square distribution. So if you take the nx minus 1 times the simple variance, that's the summation of square divided by the variance. And this summation square divided by variance, that's called a u. Adding two chi-square distribution is a bigger chi-square distribution, so that we think of chi-square distribution. So if you take this z divided by this u over the degree of freedom, have a t distribution. And why do we do all these? Because we're hoping on what we did after this division, after this one divided by this one, this is canceled. So the population standard deviation was canceled, and we end up having this, right? This is what we call the t. Looks a little bit more complex, all because of that part, right? This, if we divide this u there, divided by this, u divided by this, the denominator is a bunch of things. And we have a circle that in the red, this is the t distribution. A z distribution divided by root of the chi-square distribution, that is a t distribution. We studied this in 5.5, 5.6. So in order to simplify this, we give this a special name. We call that the pooled standard deviation. So this is called pooled standard deviation. Combined summation of square divided by the combined degree of freedom. It's called averaging of the summation square. So that's combined variance in the under the root. So the whole thing is the pooled standard deviation. We call that SP, standard deviation pulled together. SP. SP is the one that's in the denominator. So then the whole t is now simplified. And then from here, we see that t is between negative t alpha and p alpha over 2 and then positive p alpha over 2. So then the t has a natural boundary. And then multiply both side equation by the denominator, we have constructed boundary, lower bound and upper bound for mu x minus mu. So mu x mu y is between the x bar minus y bar minus t time the standard error. So that's the root of this one. It's missing the root of 1 over nx plus 1 over ny times sp. Over here is going to be t times sp times root of 1 over nx plus 1 over ny. There's an error in there as well. Any question? That's our formula. It looks a little bit different, but the underlying idea is to have a margin of errors calculated by t time. It's the variance. It's combined standard deviation. And this is case number 3. It's called pooled variance confidence interval. It does missing a root for the 1 over nx plus 1 over ny there should be a root. Okay, so this one does have the root, so that's the root part. But this is actually case number 4. Case number 4 saying, what if they don't have the same variance? So if they don't have the variance, then they have separate x squared and xy squared. They have separate variance. They are not the same. So what we're going to do is actually consider a summation of these two variants over nx. The summation under the roots in the first line of formula is the combined standard deviation. But what do? We people study the behavior of this and think of this as a special t distribution. So if you have x bar minus 1 bar divided by that big root, that's also a t distribution. However, this t distribution have a special degree of freedom. And this is the degree of freedom of that. So if we remove that common variance there, assuming they have different variance, then we have to work on the degree of freedom. Right, there's two formula. This one has a easier degree of freedom. Degree of freedom is nx plus ny minus 2, but it have a complex standard deviation that we have to find. So case number 4, when the variance are not equal, we have an easier variance formula. It's the same variance as case 1, case 2, but we have a more complex degree of freedom calculation. Any question? So basically 7.2, unlike 7.1, there's only 2 cases. 7.2, we have 1, 2, 3, 4. I think there might be a third case. There's 5 cases. That's what's making this calculation a little bit difficult because we have to look at different scenarios. Any question? We're gonna look at each situation, case 1 and 2. Okay, but case 3 and 4 and 5, we have to look at individual example to see how they match the method. That's it for today. We're gonna look at more on Wednesday. Wednesday we're back, and then I think we should pick up our quizzes. This Wednesday, let's quiz over the central limit theorem and the what's that one? Approximation of the discrete distribution. That was 5, 6, and 5, 7. We're gonna have a quiz, 1 question from 5.6 and 1 question from 5.7. Is that okay? Did you guys finish your chapter 5 homework?
No.
No? But check your assignment online and try to see if you're able to.
Would you be able to post the list of 5 and I guess all like the homework questions?
All the homework question, sure, yeah.
Because I have to go through, I can't remember which one it was. One of them had all the homework just spread out.
Uh-huh,
So I was wondering if you could do like how you do it for these. You just put all the.
okay, sure. I felt like I might have done it before.
If you have, then I just have. I'll take a look at it.
Okay, I'll do that.
Thank you.
All right, that's it for today. Thank you.
No, that's it.
You too.
I was mute.